Dear ladies and gentlemen, it's my honor to be a presenter at this year's DigiCrop conference. It's pity we cannot be all together, but we'll try to get communication through virtual presentation mode. My name is Viacheslav Adamchuk. I'm a chair of Bioresource Engineering Department at McGill University. It's in Montreal, Canada, and this presentation is done together with Roberto Bulbos, one of my PhD students. Our research team is is called Precision Agriculture and Sensor System, and is focusing on development of proximal soil and plant sensing systems, geospatial data processing and management software, as well as practical implementation of precision agriculture, including some turnkey technologies. Some of examples that I wanted to start with are relatively simple, like in this illustration, it's one of our cooperating farms that produces lettuce and other green vegetables. And our development was this little black box that actually takes weight information from the scale that we have on the platform. It's used to move pallets filled with lettuce, and we take this weight, we combine information together with geographical coordinates taken with internal GPS receiver, and through GPS modem sends this information to the server so that any manager of the farm has the ability to see what weight has been harvested from different parts of the farm in real time. With the same production environment, we were looking at the application of machine vision. That's one of the technologies that I'd like to get started with. It has enormous potential when it comes to crop sensing. What we did is using some of RGB cameras just to look at the distribution of shallots in this case by size in different parts of the field. So one of benefits of machine vision with respect to mechanical sensors that will have characteristics not only in terms of the count and weight, but also distribution of geometrical features. The same was a very crucial component of yield monitoring systems that we built for willow tree harvesting, because in this situation we were using our 3D camera with RGB with depth, and in this situation the shape of branches was also quite important because it's been used for building fences and other decorative elements. Machine vision in general can be used to assist in guiding different machines and elements of machine. And on this photograph, I show two different extremes with some of commercial cameras that been geared toward agricultural applications, like from Klaus on the left, and some of surveillance cameras that we've been using to improve machinery guidance in row crop conditions. Another mechanistic sensor that's quite important for crop is ultrasonic sensor. And in this example, we had an ultrasonic sensor in front of the forage harvester, and wired through CAN bus system of the tractor, we were able to adjust travel speed of the vehicle in response to the biomass in front of the harvester. Also, I want to mention some early research that was done in Potsdam, Germany, by some of our colleagues who worked on this pendulum system that would be used in small grain cereals to adjust rate of plant protection chemicals in accordance to the biomass that's presented. Following the same tradition of looking at biomass using different mechanistic approach, or like proximity type of sensors. This is Pasture Meter that uses array of LEDs or adds on ultrasonic just to look at the amount of biomass produced in different parts of the field. Finally, ultimate goal of manual plant-related research in commodity crops would be sensing crop canopy to identify stresses during vegetation stages. And this prototype that have been used in sort of different type of research for quite a few years is the integration of three different measurement principles, including ultrasonic sensor, optical reflectance sensors, and thermal sensors, just in one package, because that's how we can differentiate different type of stress in the crop. The reason we're interested in optical sensors because of the light reflectance curve that has a very characteristic behavior for vegetation with blue and red absorption and increased reflectance in green and much high increase at the infrared part of the spectrum, and of course red edge part of the spectrum is the most interesting when it comes to detecting different nutrient and water stress situation in plant and during growing season, and this technology has been successfully used for variable rate in-season nitrogen management in response to crop performance. Depending on the value of the sensors that presented, it at later vegetation stage, it's also possible to use ultrasonic sensors to achieve variable rate management of nitrogen fertilization. But at early stage, there is a belief that fluorescence sensors can provide relatively accurate data related to stress, which also comes at a relatively high cost. So we have fluorescence sensors at high end, then we have optical sensors, and then we have ultrasonic sensors, and all have own pros and cons, and looking at entire array of opportunities. It's something that most promising strategy. In terms of mechanistic sensor, also LiDAR sensor is quite important, and LiDARs have been used as a key plant sensing element. But in our research, we were looking at the opportunity to reduce the cost of sensor system, and we used a point-based LiDAR from Keynes Technologies and developed a stepper motor-based operation where we could look at individual crop canopies, like we were looking at spinach to identify fresh biomass while in situ. Thermal imagery, it's another important characteristics because combining thermal characteristics and biomass characteristics, we can, and like chlorophyll related characteristics, we can separate water stress from nutrient stress, which is one of important challenges when it comes to crop canopy sensing. So to achieve this at a higher level, especially for some of breeding programs, our faculty is in the process of setting up state-of-the-art plant phenotyping platform that integrates kinetic fluorescence, hyperspectral imaging, LiDAR sensing, thermal sensing in one package. But to address needs of wide-scale breeding programs, we also looked at a lower level rapid phenotyping system that's based on crop circle sensors from Holland Scientific and integrated with ultrasonic sensor. And I have my student presenting this for you.
My name is Roberto Huelvas, and I am a PhD student at McGill University and member of the Precision Agriculture and Sensor Systems research team. My research currently focuses on plant phenotyping. The availability of large datasets and the automation of the data collection process can help with the challenges the agricultural industry has to face today. In particular, I am developing a rapid phenotyping system with the desired characteristics shown here. This is the conceptual design of the system. A key advantage of this design is that it can be used with large and small agricultural vehicles, potentially benefiting all types of growers. Another important feature of this system is that it can diagnose the misalignment between the sensors and the canopy of the plants using computer vision. This information could also be used as feedback for an auto-steering module to minimize the error. The system is equipped with the following sensors: ultrasonic, multispectral, camera, environmental, and GNSS. Here we have a diagram of how the different components will communicate with each other. The terminal in the center runs the software built to control the system. This animation shows typical use of the software with the sensor readings being displayed. The data is then saved in the hard drive of the terminal for further analysis. In the top left corner, there is a map of the locations where the vehicle has recorded measurements. Once a dataset has been prepared, there are many ways it can be analyzed. The basic assumptions for this project are that the phenotypes of a plant are the result of an interaction between its genome, its environment, and the farm management practices to which it has been exposed. In the context of plant breeding, it is important to isolate the effect of the genome from the resulting phenotype in order to select the genetic material with desired behavior. As a first experiment, a manual setup was built that included the same type of sensor as the system developed in this project. A field of white beans was used to collect data over the summer of 2019. This first experiment included 11 cultivars or varieties, 22 plots, and 4 dates of data collection. The goal was to determine the capability of the sensors to differentiate the bean varieties based on their performance. An illustrative example was to consider if they were above or below average in terms of plant vigor. Different statistical methods and models were used in the analysis. The preliminary results show that there was potential to find significant difference in between the crop varieties for specific dates, but it was not consistent throughout the growing season. Ultimately, it was possible to rank the cultivars based on different metrics extracted from the models that had been used in the analysis, and summarize those findings in the categories that had been defined at the beginning of the experiment of above average, average, and below average. However, these results by themselves are not statistically significant. After that, a prototype of the design system was assembled and tested over this summer. This time, the experiment included more than 20 cultivars and 200 plots, measured over 11 dates. This experiment was only made possible by the higher throughput of the system. While the data analysis of the 2020 dataset has not been completed yet, there is great potential for the technology developed, and its application might benefit growers and breeders. Thank you for listening.
Well, thank you, everybody, and this would be a place to have a discussion and answer any questions. But considering virtual format of this conference, please don't hesitate to email me at the email provided on the screen if you have any comments, questions, recommendations, and thank you very much.